Watch me solve 11 equations where each one gets more difficult than the previous one. Let me know in the comments how far you could get through these 11 equations. Here's the first equation. When solving any of these equations, we're really just trying to find out what value of x makes the left side of the equation equal to the right side. We're starting off with a really simple linear equation where we can just use inverse operations to isolate the x, and then that'll be the answer to the equation. Let me start by rewriting the question. I'll try and isolate the term that has the x by getting rid of the minus 7 by doing the inverse of subtracting 7, which is adding 7. I'll make sure I add 7 to both sides of the equation. I do that because on the left, minus 7 plus 7 cancels out. I'm left with 3x equals 18. And then to isolate the x, I'll do the inverse of multiplying by 3, which is dividing by 3. I make sure I do that to both sides so it stays balanced. 3's on the left cancel. And I get my final answer of x equals 18 over 3, which is 6. Here's question number 2. This is another linear equation, so not too difficult yet. You might be tempted to try and distribute this 1/3, but I think it'll be easier if what I do is try and get rid of that fraction right away. I'm going to multiply both sides of this equation by 3. The left by 3, and the right by 3. The reason I do that is because on the left, I have a 3 divided by 3, which cancels. So now I have no fractions left. On the left side of the equation, I just have 1 times x plus 9, which is x plus 9. On the right, I have 3 times x plus 1. I'll distribute on the left side to get 3x plus 3. Now I want to get both of the variable terms on one side of the equation and both of the constant terms on the other side of the equation. I'll bring the constant terms to the left, so I have 9 minus 3 on the left. The variable terms on the right, I have 3x minus 1x. 9 minus 3 is 6. 3x minus 1x is 2x. I'll isolate the x by doing the inverse of multiplying by 2, which is dividing by 2. So I have 6 divided by 2 equals x. So x is 3. Here's our third equation. This equation is quadratic, so we may get up to 2 answers to this equation. When solving any quadratic, it's usually good to set it to 0 first. So I'll start by moving that 12 to the other side, so I have x squared plus 4x minus 12 equals 0. I'll now solve this quadratic by factoring. I notice that the a value is 1, so to factor it, I just need to find numbers that multiply to the c value of negative 12 and add to the b value of 4. The numbers that satisfy that product and sum are 6 and negative 2. So that quadratic factors to x plus 6 times x minus 2. Now that it's in factored form, I can use the zero product rule that tells me the product of two factors is 0 if either of the two factors are 0. So if x plus 6 was 0, the whole product would be 0. Or if x minus 2 was 0, the whole product would be 0. X plus 6 would be 0 if x was negative 6. And x minus 2 would be 0 if x was 2. So we have 2 solutions to this equation, negative 6 and 2. Here's equation number 4. Once again, this is a quadratic equation, so I'll start by setting it equal to 0. Now I'm going to want to get this into factored form if possible. I'll start by taking out a common factor of 2. When I divide all 3 terms by 2, I get 5y squared minus 8y plus 3. Now the quadratic in the brackets, the a value is not 1, it's 5. So if this is factorable, I'm going to have to factor it the long way by decomposition. I need to find numbers that multiply to a times c, 5 times 3, which is 15, and add to the b value of negative 8. The numbers that satisfy that product and sum are negative 5 and negative 3. So what I can do is split the middle term, negative 8y, split it into negative 5y minus 3y. And now I continue factoring by grouping. I take a common factor from the first 2 terms. I could common factor a 5y, and then have y minus 1. And then from the last 2 terms, I could common factor a negative 3, and then have y minus 1 again. Notice the common binomial of y minus 1. I could common factor out that common binomial. And once I remove that common binomial as a factor, I'm left with 5y minus 3. That's now fully factored. Using the zero product rule, I know the product would be 0 if any of the factors would be 0. y minus 1 would be 0 if y was 1, and 5y minus 3 would be 0 if 5y was 3, and if y was then 3 over 5. There's my second answer. Here's the fifth equation. This is our first exponential equation. Notice I have two powers equal to each other that have different bases, but I can rewrite the base of the power on the right, 8, so that it has the same base as the power on the left. So I can rewrite 8 as a 2 cubed. On the right, I now have a power of a power. When you have two exponents on top of each other, you can just find their product. So it's 2 to the power of 3 times x minus 2. Make sure you distribute the 3 to the x and the negative 2 to get 3x minus 6. Now that I have power equals power, where the bases of those powers are equal, I know the only way this equation could be true is if their exponents were equal to each other. So I can just set the exponents equal and solve. Move the 3x to the other side, and I'm left with x equals negative 6. There's my solution. Here's equation 6. We're at the midway point. We once again have an exponential equation, but if we look at the bases, it would be very difficult to rewrite those as powers with the same base. So we'll use a different strategy. I'm going to take the common logarithm of both sides of this equation. I do that so that I can take the power of the argument of the logarithm, use the power rule, which tells me I can write it as the coefficient of the log. This gets my unknown out of the exponent. I'll expand both sides of that equation by doing 3x times log 4 and negative 1 times log 4 on the right, x times log 5, and 2 times log 5. So I have 3x log 4 minus log 4 equals x log 5 plus 2 log 5. I now want to get both terms that have an x on the same side of the equation, and both terms that don't have an x on the other side of the equation. I'll bring the terms with the x to the left. So on the left, I have 3x log 4 minus x log 5. On the right, I have 2 log 5. But remember, I could take that coefficient of 2 and write it as the exponent on the argument of the log. So that'd be equal to log of 5 squared, which is log 25. So I'll just say log 25. Bring over the negative log 4, becomes plus log 4. Now what I want to do, I notice both terms on the left have an x, so I'll common factor out an x, which will give me 3 log 4 minus log 5. On the right, I have 2 logs being added. I can use the product rule of logs, which tells me I can write it as a single log by multiplying their arguments. 25 times 4 is 100. Oh, and log 100, what exponent goes on 10 to get 100? That's just 2. On the left side of the equation, I'm missing a bracket there. I want to combine those two logarithmic expressions. Before I can do that, I would have to take that coefficient of 3 and make it the exponent on the 4. So 4 cubed is 64. When two logs are being subtracted, we write it as a single log by dividing their arguments. So it would become log of 64 divided by 5. I can isolate x just by dividing that logarithm to the other side. So I have x equals 2 divided by log of 64 over 5. That's the exact answer to this equation. If we want an approximate answer, it's about 1.806. Here's equation 7, our first trig equation. Trig functions are periodic, so there's going to be an infinite number of answers to this equation. But we'll start just by finding the two answers that are between 0 and 2 pi. I need to isolate that sine x first. So I'll have sine x equals negative 1 over 2. I see that I have a negative sign ratio, so I'm going to draw a Cartesian grid and figure out where my answers are going to be. Because my sign ratio is negative, I know sine is negative in quadrant 3 and 4 based on the cast rule, so I know I'll get an answer in both of those quadrants. I'll draw a terminal arm in both of those quadrants, and I know those terminal arms will have the exact same reference angle. And if you know your special triangles, remember the half equilateral special triangle with side lengths 2, 1, and root 3, and angles pi over 3, pi over 6. Notice that sine from pi over 6, right, sine is opposite over hypotenuse, is 1 over 2. So if I place that reference angle of pi over 6 in quadrant 3 and 4, I will get a sine ratio of negative 1 over 2. So I can label this reference angle in both of those quadrants as pi over 6, and then calculate the principal angle to get to each of those terminal arms. My first answer would be past pi by pi over 6, and my second answer would be pi over 6 less than going a full 2 pi. So let's do those two calculations. Answer 1, pi plus pi over 6. So answer 1 is 7 pi over 6. Sine of 7 pi over 6 is negative a half. And my second answer was pi over 6 less than 2 pi, so 2 pi minus pi over 6, which is 11 pi over 6. So 7 pi over 6 and 11 pi over 6 are the two answers between 0 and 2 pi. Like I said, there's an infinite number of answers. We could find coterminal angles to both of those by just adding 2 pi to them as many times as we want, and we would get more answers to the equation. So for both of them, I could just say we could add 2 pi k times as long as k is an integer value, and I would get more answers. There we go, that's the 7th one done. You can see the difficulty is really starting to ramp up. Here's the 8th equation. This is a polynomial equation. To figure out when a polynomial is 0, we're going to want to get it into factored form. So I have to start by testing for zeros of this function so I can figure out what a factor of this is. Possible zeros of a polynomial function are factors of the constant term at the end. So factors of 18 are plus or minus 1, 2, 3, 6, 9, or 18. I just need to find one value that makes that polynomial be 0. And then I can divide by its corresponding factor to start getting it into factored form. So I'll do a test. Let me test out negative 1. If I evaluate this, I would get 1 plus 1 minus 11 minus 9 plus 18. And that equals 0. So because negative 1 makes that polynomial be 0, I know that's one answer to my equation, but to get the rest of the answers, I should divide that polynomial by the factor that has a 0 of negative 1. X plus 1 has a 0 of negative 1, so x plus 1 is a factor of the polynomial. So what I'm going to do is divide that polynomial by x plus 1, and I'll do that by synthetic division. The 0 of the divisor is negative 1. The coefficients of the polynomial are 1, negative 1, negative 11, 9, and 18. If I run the synthetic division, bring down the 1, multiply by negative 1, add in that column, multiply by negative 1, add, multiply by negative 1, add, multiply by negative 1, and I get a remainder of 0, and the rest of the numbers are the coefficients of each term in my quotient. So I could rewrite the original equation as a product of x plus 1, which was the divisor, and the quotient, which was x cubed minus 2x squared minus 9x plus 18. And now I notice that the degree 3 polynomial I have as my second factor, I could factor that by grouping. I could take a common factor from the first two terms and a common factor from the last two terms, and I'll end up with a common binomial. I'll take out an x squared from the first two terms and have x minus 2. Take out a negative 9 from the last two terms and again have x minus 2. I have that common binomial of x minus 2. When I factor that out, I'm left with x squared minus 9. And that x squared minus 9 is a difference of squares. It's an x squared minus a 3 squared. So I can factor that to x minus 3 times x plus 3. Now that the polynomial is fully factored, I know any number that would make any of those factors be 0 is a solution to the equation. So looking at my factors from left to right, the zeros would be negative 1, 2, 3, and negative 3. So all of those are answers to the original equation. Here's the 9th equation. This is the first logarithmic equation. Our unknown is in the argument of a logarithm. I notice that I have two logarithms with the same base that are being added together. I could combine them together by multiplying their arguments. X times x minus 4 is x squared minus 4x. Now this logarithm is the common logarithm. If we don't see a base, it's 10. And a logarithmic expression is a way of getting the exponent, 1, that goes on the base of the logarithm, 10, to make it equal to the argument. So I could rewrite this in exponential form as 10 to the power of 1 equals x squared minus 4x. This is now a quadratic equation to solve. I'll set it to 0 by moving the 10 over. I have x squared minus 4x minus 10. Now this quadratic It's not factorable. Nothing multiplies to negative 10 and adds to negative 4. So that means if there are zeros, there will be irrational zeros, and we'll have to get them using quadratic formula. Quadratic formula uses the a, b, and c values of the standard form quadratic. It'll be x equals negative b, so 4, plus or minus the square root of b squared, so negative 4 squared, minus 4 times a times c, all divided by 2 times a. I'll simplify underneath the square root. Underneath the square root, I have 16 plus 40, that's 56. This radical expression can be simplified. There is a perfect square factor that goes into 56. 4 goes into 56 14 times, so I can split this into root 4 times root 14. But the square root of 4 is just 2, so I'll rewrite that as 2 root 14. Now both terms in the numerator are being divided by 2, so I could write this as 4 divided by 2 is 2, plus or minus 2 root 14 divided by 2 is just root 14. So I have two answers to this equation, x equals 2 plus root 14, and also x equals 2 minus root 14. But when solving a logarithmic equation, you have to understand that the argument of a logarithm is restricted to being greater than 0. So if either of the answers we got make either of the logarithmic expressions undefined by making the arguments less than or equal to 0, then we call it an extraneous root. Notice that 2 minus root 14 is going to give us a negative answer, so of course that's going to make both of these log expressions undefined. So 2 minus root 14 is an extraneous root. So the only real answer to this equation is 2 plus root 14. Here's the 10th equation, only 2 equations left. This is another trig equation, but this one is especially difficult because we have 2 different trig functions in this equation. I'll start by using an identity that tells me that secant squared x is equal to tan squared x plus 1. I'll distribute the 2 to get 2 tan squared x plus 2 minus 3 plus tan x equals 0. I'll rewrite this in standard form and collect the 2 minus 3 together. I might at this point actually also use a let statement. I'll say let tan x equal k. That'll make this equation look easier. It's just 2k squared plus k minus 1 equals 0. So that looks like an easy quadratic to solve, where I would want numbers that have a product of a times c, so a product of negative 2, and a sum of the b value, which is 1. The numbers that satisfy that product and sum are 2 and negative 1. I'll factor that quadratic by decomposition. I'll split that k into a 2k minus 1k, and then factor by grouping. Take it a 2k from the first 2 terms, take out a negative 1 from the last 2 terms, take out that common binomial of k plus 1, and see we actually get 2 answers for k. We get k equals negative 1 and k equals a half. But remember, those k's are actually tan x. So we're about halfway done this question now. Let me make some more room. Like I said, those k's are actually tan x, so I actually have tan x equals negative 1 and tan x equals a half. Let me draw a Cartesian grid for both of those. If I focus on the equation tan x equals negative 1, I have a negative tan ratio, which happens in quadrants 4 and 2. So I'll draw a terminal arm in both of those quadrants. And if you remember your special triangles, I can get a tan ratio, opposite over adjacent, of 1 over 1 when the reference angle is pi over 4. I know the reference angle in both of those quadrants is going to be the same. So the reference angles are both pi over 4. And I know the tan ratio is going to change to negative because it's in 2 quadrants where tan is negative. So my first answer goes from the initial arm to that first terminal arm, which is pi over 4 less than pi. So I'll say x1 equals pi minus pi over 4, which is 3 pi over 4. And x2 is pi over 4 less than 2 pi. So I'll say x2 equals 2 pi minus pi over 4, which is 7 pi over 4. Notice any answers to an equation that involves tan are going to be separated by a difference of pi. Right? To get from 3 pi over 4 to 7 pi over 4, you can just add pi. And that's because the period of a tan function is pi. So I could get infinitely many more answers by continuing to add pi. So I could summarize both of those answers together. I could just say x equals 3 pi over 4 plus add pi as many times as you want, as long as k is an integer value. How about the equation tan x equals a half? That's a positive tan ratio. Tan is positive in quadrant 3 and 1. I'll draw a terminal arm in both of those quadrants. I know those principal angles are going to have the same reference angle, and I can't make a tan ratio of a half from a special triangle, so I would use my calculator to find an approximate answer. I would do inverse tan of a half, and it's about 0.46. So I know that's the reference angle for both of those principal angles. So my third answer, x3, is 0.46. My fourth answer, which goes all the way to here, goes past pi by 0.46. So pi plus 0.46, it's about 3.60. Notice once again, the relationship between these answers is that I just add the period of tan, which is pi. So I could summarize that full set of answers by saying x equals my first answer, 0.46, plus pi k times, where k is an integer. Here's the 11th equation, the very last one, the most difficult one. This is an exponential equation where you may not know where to start. There's actually a hidden quadratic here, and you'll only be able to see it if we multiply both sides of this equation by 2 to the x to start with. On the left side of the equation, let me distribute that 2 to the power of x to both terms, and you'll have to remember your exponent rule that says when multiplying powers to the same base, you add the exponents together and keep the base the same. So when I do 2 to the x times 2 to the x, I keep the base the same and add the exponents. X plus x is 2x. When I distribute to the second term in the brackets, I keep the factor of 12, and 2 to the x times 2 to the negative x, those powers have the same base, so I can keep that base of 2 the same, add the exponents, x plus negative x is 0. On the next line, I'm going to do a couple things. This 2 to the power of 2x, I'm going to use the power of a power rule and rewrite that as 2 to the x squared. 12 times 2 to the 0, well, I know 2 to the power of 0 is 1, so 12 times 1 is just 12. Now I'm going to bring this term to the left side of this equation. And now I'm going to use a let statement so you can see the hidden quadratic. Let's let 2 to the power of x equal k. So what I have is k squared minus 7k plus 12 equals 0. That quadratic I could factor. The numbers that multiply to 12 and add to negative 7 are negative 3 and negative 4. So the solutions to this equation are k equals 3 and k equals 4. But remember, those k's are actually 2 to the power of x. So I have 2 to the power of x equals 3, and 2 to the power of x equals 4. Well, 2 to the x equals 4. That's easy to solve. What exponent goes on 2 to get 4? That's 2. 2 squared is 4. How do I find what exponent goes on 2 to get 3? I'll have to use a logarithm. I can say the exponent equals log base 2 of 3. That'll find me what exponent goes on 2 to get 3. As an approximate answer, that's about 1.58. There you have it. Through all 11 difficulties of high school math level equations. Let me know how far you got and which ones you found the most difficult. Jensen